Alright, so let's look at this quadric surface there. Let's look at this paraboloid here. So if we look at this paraboloid right here, notice that if we pick up a point P there on that paraboloid, point P there, and we want the gradient of that paraboloid at a point P, we want to find the tangent line to that paraboloid at point P. Notice that here you can have like a tangent line that touches P like this. You can have a tangent line as being something like this. Notice that it touches that paraboloid at one point, and then you can also have a tangent line like this going in that direction, and it only touches the paraboloid in one direction. It's hard to see because that thing is technically in 3D, but picture it as a line just passing through, touching that paraboloid at a point P and just crossing through it. Only intersect that paraboloid at a point P. And then you can also have like a line here, let me just say, coming out of the screen like this, just having a line shooting out of the screen like this, heading that, and then that will also be a tangent to that paraboloid at a point P. Notice that you can have as many tangent lines towards this paraboloid at a point P, but then we need to like if we want our tangent line, then obviously we need to like specify the direction in which we want the gradient of that. Remember, the gradient will be the slope of that tangent line, and if we have a tangent line, we'll basically have a slope. But notice that here these two lines have completely different slopes. So we'll have a slope. The slope will have a certain magnitude in a certain direction. That's what I'm getting at here. So allow me to introduce you to a concept of a directional derivative. So the idea is like, if we want the slope at P, we have to specify where, in what direction do we want that slope. So let's say we want the slope at P in the direction of Q. So the idea is that since this is a 3D surface here, or a 3D, it's technically given by z being some function of x and y, so it's technically available in like two you're basically mapping two variables against the z-axis, two variables against one, so z is equals to some function of x and y and stuff like that. So, and then here, if you look here, if you project that onto an xy coordinate system, then you have something like this. So the projection of P will just be P prime, and the projection of Q will just be let's call that Q prime. So the projection of Q will technically be Q prime, and then you have something like this. So you technically have the direction of PQ in that way. Notice that here, since this is in 3 dimension, we can have the coordinates of P being x naught, y naught, and z naught, like that. And that projection, we basically fix the value of z. We project that into the xy plane, that means z will be equals to 0. So that means that P prime, we're just going to neglect the value of z. That will just be x naught, y naught. Similarly, we can do the same with Q. Notice we can give Q the coordinates x, y, and z, and then the projection of Q will just basically be x and y in that way. We're just basically like projecting this into a xy plane. So when we have that, notice that here we can give off, if you remember from 1644, and then you have P prime, Q prime, that vector here. Remember how you find a vector? You take the terminal and subtract the initial from there. So technically you just have like terminal minus initial. So you just have x minus x naught, and then you have y minus y naught as, y minus y naught. Then you have something like this. So this is our vector. Okay, so now the idea is now we can have like our unit vector. We can have a unit vector here that is parallel to this one. So we can basically, we're just going to give our unit vectors we're going to give our unit vector components a, b, and what we know about our unit vector is that it has a magnitude of 1. But notice that here we say that our unit vector is parallel to this vector here. So if our unit vector is parallel to this one here, that means that we can express P prime Q prime, that vector there, as a scalar multiple of this one with u. A scalar multiple of our unit vector will just technically give us P prime Q, the vector P prime Q prime. And then in that way, it's just a definition from like 1644. Check those videos out if you still don't understand about parallel vectors, because those are basically the introduction to that. Vector analysis arises from that, so you need to have a strong background of vectors in order to understand these things. But the idea here is that if these two vectors, P prime, Q prime, is parallel to our unit vector, so that means that we can express PQ, this vector here, as a scalar multiple of the unit vector multiplied by some constant, that scalar multiple here. But we know that our unit vector is technically given by is technically given by AB in that way. So that means that we can express this one as this. So before I express this one as just HA multiplied by HB, notice that here, the length of this one is just 1. But the length of P prime Q prime here will just technically be equals to H, because it's 1 multiplied by that H. It's just going to be H units long. So this vector here, this one is just going to be H units long from our definition here. It's just technically we let our unit vector be P prime Q prime be a scalar multiple of that unit vector, and using this one we can then say that this one is technically going to be H units long. Nothing special about that. So, and then, but earlier we denoted this vector as this, but now we give it in terms of like a unit vector. So notice that here this is technically this, so that means that x minus x naught will technically give us HA, and then y minus y naught will technically give us HB. In that way we can solve for x and then say x equals x naught plus HA, and then we can say y is equals to y naught plus HB. In that way then we have something like this. But what do we want exactly? We want the gradient at this point, and then in simple terms, we're just looking for the derivative in that point. Remember, a derivative just kind of like represents a slope of a function. Okay, so I think before we get any abstract on this, let's just revisit like our high school math for just a sec. Remember, like when you have a straight line like this, the gradient of that is technically equals to the derivative of that. Remember, the gradient at that point is technically equals to the derivative. So at that point specifically, that's just the idea. The first derivative kind of like denotes the slope. So the gradient of this line is basically equals to the rise of that function for how much you move on the width of that, how much you move on the x-axis, and how much you rise on the y-axis. And notice that this graph is just y equals f of x. So this is just change in f over how much x changes. So just basically, if we're starting from the origin, that will just be x in that case. And then that's the idea of a derivative, that the derivative is just kind of like represents a slope. This is the rise of a function divided by how much you move along the x-axis. In 3D, we keep the same definition, and that will just be the derivative of that at whatever point on the function is. In 3D, we kind of like keep the same definition. Remember, our function will technically be given by z equals f at xy. So that means the rise of that function is technically along the z-axis like that. We can say this is y and this is x, but you can keep, remember, like your coordinate systems, they don't really matter. Your axis, you can switch this, you can reflect this axis any way you want. You can keep the z in this direction, doesn't really matter, but it's easier to understand in this way because it's easier to identify what I'm referring to when I say a rise in something. So let's say we have a line in that coordinate system. Notice that here the rise of that function is technically equals to z. And if we keep the same definition that the gradient is just that, so we're just going to have the change in z over how much we move along the x and y coordinate system. How much we move, and then how much we move in the x and y coordinate system will basically be given by whatever length that you have here. So whatever length that you get here, let's say this is point A over AB, then that will just be the magnitude of AB in that sense. You can say you have a vector and that's still fine. So from high school stuff, we now go to 3-dimension. We define the gradient and something like this, and then we can get back to our thing here. Since we're looking for the directional derivative of that, notice that you're always going to keep your vector as a unit vector in that case. Whenever you're looking for like a directional derivative, your vector must be converted back to a unit vector. So we just do u f at x naught y naught. Okay, before I go there, let's just start with that. The gradient will technically be the change in z over how much do we move along the xy coordinate system. Notice that I said this length here will technically be just h, so we just only move h units in the xy coordinate system. So but we know that for a derivative we want the slope at a certain point, we want the exact slope, so we're just going to denote that with like a limit h must technically approach 0. So then you have a limit when h goes to 0 of, remember, changing z is just going to be z minus z naught in that case over h. And what is z? Z is technically f at x, y. And then z naught will technically be f at x naught, y naught in that sense. So, but keep in mind, I said that this will technically be f at x, y minus f at x naught, y naught in that case over h. But I defined something here. I said x equals x naught plus ha. So you're just going to basically replace that with, you're going to replace this x with x naught plus ha, and you're going to replace this y here with y naught plus hb, because that's just what we got from here. So now that means that you have f at x naught plus ha, y naught plus hb minus f at x naught, y naught in that sense. Y naught all over h when h goes to 0. So that's just your definition of a directional derivative. So it's defined by something like this. Notice that this is by definition. Remember, we have like certain rules. I'm just gonna keep, like, nothing has changed really. We're just keeping the same stuff. Remember how we used to find the derivative of f of x? That this is the limit when h goes to 0 of f at x plus h minus f at x all over h. We evaluate the limit when h goes to 0. This was not our only way of finding the derivative. That's where I'm getting at. We also had certain rules on how we find derivatives. Keep in mind, if we have like f of x equals 2x squared, remember we can still find the derivative without using the definition, and we use like the power rule on that, and then you're just gonna have 4x. That was our derivative. So the mathematics hasn't changed. Really, we can also come up with a way we can rewrite this in a way that we don't actually need to evaluate the limit. Okay, suppose that the limit exists. That means that the directional derivative will be given by this. So if we are certain that the limit exists, that means that we can simplify further here. We can just rewrite this without having to evaluate the limit. So here's what we do. We can say, since we're evaluating the limit when h goes to 0, we can suppose that g at h was our function f at xy. Now we just define our function g at h being f at xy. In that way, we're just basically going to apply the chain rule. I know I haven't done a video on the chain rule, but here's the idea. If you're going to find the total derivative of g with respect to h, you're going to have to find the partial of f with respect to h. Sorry, with respect to x, since x is our variable, and we're going to assume we know that x is a function of h as well. X is a function of h. So that means that we have to take the total derivative of x with respect to h plus the partial of f with respect to y, and y is also a function of h here. You can see that. Then we take the derivative of that with respect to h. And then we just find that. We know that we denote this one as just fx. And what's dx dh? X is this one. Dx dh is just going to be a. I'm sure we can derive this. With respect to h, this one is constant. The derivative of this one with respect to h will just be a. And then similarly, we can, the derivative partial of f with respect to y is just going to be fy. And then dy dh, that's just technically going to be b, because this one is constant here. So you're just going to derive that part and you just get b. So then you have g prime at h. But remember, here we were evaluating the limit when h goes to 0. Okay, first let me just write that down. So this is just, let me just write in full notation, because you might not get what I'm getting at here. So this is f at x evaluated at xy multiplied by a plus the derivative, the partial derivative with respect to y of f evaluated at xy, and that's just going to be b, like that. This is what I basically mean, since it might be hard for you to understand when I wrote something like this. So this is what we have. But the idea is now h must go to 0. So that means that this one can be defined as g prime at 0. The directional derivative of that will be g prime at 0. What's g prime at 0, by the way? If we check g prime at 0 here, that's where h goes to 0. So what happens to x when h goes to 0? Let's go back here. X is this one. If h goes to 0, this term disappears. Then you just have x equals x naught. So you're just going to have partial of f with respect to x evaluated at x naught. What happens to y when h goes to 0? This term goes, and then you just have y naught. So then you just have x naught, y naught, something like this, multiplied by a plus partial of f with respect to y at x naught, y naught, like that. And then you just have this. So that's what we have, which is basically like simple really. So that means that we can rewrite this instead of evaluating the limit. Then we can just rewrite this directional derivative as something like this: du f at x naught y naught being equals to the partial of f with respect to x evaluated at x naught y naught multiplied by a, and then plus the partial of f with respect to y evaluated at x naught y naught multiplied by b, whereby a and b are just basically like the components of the unit vector in the same direction that you're looking for the directional derivative at. So what does this mean? Since you have like this being like this, we know that a and b come from a vector, but we know that the directional derivative, by just looking at the formula, it's a magnitude, right? This is a magnitude. How do we multiply vectors such that you just get a magnitude? We technically just find the dot product of that. You can do the mathematics and you'll find that you have the vector f at x naught, partial of f with respect to x at y naught, at x naught y naught, partial of f with respect to y at x naught y naught, dot that with your unit vector ab, and that's your directional derivative. This thing, notice that it represents a slope, but now we give it a direction because we know that a vector technically has a direction. But what do we know about a derivative? It represents a gradient. So we know that this vector here will just be a gradient vector of f, or you can just call it del f. That will just be our gradient vector of f, or gradient of f. So the gradient of f is technically given by this vector here. Okay, so let's go higher. Let's keep escalating this. See here, if you're dotting two vectors like this, okay, I know most of you might have forgotten this stuff. Let's go back a bit. If you have v1, vector v1, dot that with v2, or just the scalar product of that, this is equals to the magnitude of v1, dot that with, multiplied by the magnitude of v2, multiplied by the cosine of the angle between them. So this is by definition the dot product. That's the formula for the dot product. So notice here there's something here. We can therefore rewrite this again and say that this is just the magnitude of our gradient vector multiplied by the magnitude of our unit vector multiplied by the cosine of the angle between those two vectors. What's the magnitude of a unit vector? A unit vector is a vector of unit 1, or of length of 1 unit. So that means that we can therefore say that we have something like this: the magnitude of the gradient of f, the gradient vector of that, and then you just have the gradient vector multiplied by cosine of the angle between the unit vector and the gradient vector. But this one we know it's fixed. This one we know that it's fixed. It's just a certain value. It's fixed. The only thing that can change is cosine of the angle between those two vectors. But here's the thing. Notice that we can find the maximum. We can find the maximum value of the directional derivative. So let's just do that, because cosine is defined. Cosine is a range between like two defined values. If you graph the graph of cosine, then you have something like this. It's a wavy function. Then you expect something like this continuously in whatever direction in that. Let's just limit to this region here. So if you keep your graph at this interval here, notice that here cosine is maximum at 1. And if cosine is maximum at 1, that's where our angle is 0 degrees. And if the angle is 0 degrees, what does this tell you? this tell you that if the angle between, remember our angle, if you have v1, vector 1 and vector 2 in that direction, this is the angle between those two vectors. And if this theta tends to go to 0, that technically implies that this v1 and v2 are technically in the same direction. If you look at that, v1 and v2 are in the same direction. So that's where we'll find the maximum of that, the maximum value for the directional derivative. It will maximize where cosine theta is equals to 1, or you can just say where theta equals 0, whereby the gradient vector and the unit vector are in the same direction. You can say it's where, because like it's the language of math is beautiful though. You can just say where the gradient vector, this one, is parallel to you. So they're parallel at 0 degrees. But saying parallel, it kind of like implies the other thing, because like even if the angle was 180 degrees, it will still be parallel. But then let's just leave it. Let's just know that we have this. So what's the maximum value for the directional derivative? The maximum value for the directional derivative will be it equals to just changing f, the magnitude of that directional derivative. So whenever they want you to just find the maximum directional derivative, they mean like at a certain point, then they just mean just find the magnitude of the gradient vector, or find the magnitude of del f. So that's it. So that's all about the directional derivative. That's the idea that you must familiarize yourself with. And so let's just try one question and see what's happening. So let's say we have f at xy equals something like, let's say, just think of any surface. So you can say 2x squared y plus 2xy squared. So find, if our function is this one, and we want to pick up a point on that function. Let's say we pick up a point P. That point, let's say, okay, let me just say this. Find the rate. Okay, let me just start like this. What is the okay, let me think. Okay, so let's go back. Find the rate of change of f at a point. Let's pick up a point P1, 1. Find the rate of change of f at a point 1, 1 in the direction of find the rate of change of f at a point 1, 1 in the direction of q, and let's pick up a point half and 1. It's fine like this. It can be any point really, but this is just for exercise purposes. So if you want to find the rate of change of f at a point 1, 1 in the direction of q, they just technically mean find the directional derivative of that. Okay, so first things first, find that vector there. PQ, vector PQ will just technically be terminal minus initial. Terminal half, initial 1. Half minus 1, that's just going to give us minus half. 1 minus 1, that technically gives us 0. And what's the magnitude of PQ? The magnitude of PQ, vector PQ, that one, is just technically going to give us, remember how you found the magnitude? You just sum up the squares of the components. So that will technically be minus half square plus 0 square. And if you add the third component, that's where, but you know how to find the magnitude. It's 1644 stuff, so then you just have half. That's the magnitude of PQ. Now you want to find the unit vector in the direction of PQ, so that's just PQ over the magnitude of PQ. So you just divide the components by the length. So what's minus half divided by half? That's 1. What's 0 divided by half? That's 0. So your unit vector is this, right? So you find that unit vector there. And remember how else you can find how you find the rate of change of a function? This is our formula here. It's this one. So technically that implies that that you have to find the direction. I mean, you have to find the partial derivatives and evaluate that point P. Okay, so let's just do that. So what's the partial of f with respect to x? X not y, at x and y. This technically gives us, you derive this with respect to x, so that's just technically going to give us 4xy plus 2y squared. Then you evaluate the partial derivative at a point 1, 1. 1, 1, and then you're just technically going to get a 4 plus 2, which is 6. And then you find it's x here. Then you find the partial of f with respect to y, and then you're just technically going to give like 4x squared plus 4xy. And this is what you have. Alright, so I see here I made a mistake. It's supposed to be 2x squared, because we're just basically deriving with respect to y, so we're just gonna end up with 2x squared. Okay, so be careful when you make this, because these types of mistakes, they can happen. And then partial of f with respect to y at a point 1, 1, that's technically gonna give us 2 plus 4, which gives us 6 again. So what's the directional derivative of that? The directional derivative of that, let me not use the gradient vector, let me just use this formula here, the one before we introduce the gradient vector of that. So we have du at a point 1, 1, that's just going to be equals to the partial of f with respect to x at 1, 1, multiply that with a, and our a is technically equals to 1 in that point, so it's just going to be 1 plus the partial of f with respect to y multiplied by b, and b in that case is technically 0. Our unit vector says that's 0. So what's your directional derivative? It's just going to be 6, because this one is 6 by 1 and then it's 6. This one is just going to be 0 since we're multiplying everything by 0. So the derivative of f at a point 1, 1 in the direction of half 1, that's just going to be equals to 6. So we found the gradient in that direction. And then what if we ask you, what is the maximum rate of change of f at a point P? What is the maximum? Let me just do that. What is the maximum? Let me ask the second question. Let's say this one is the first one. What is the maximum? The maximum rate of change of f at a point P. At a point P. So what did I say? I said whenever they want you to find the maximum rate of change, that's where you have to find the magnitude of your directional derivative at whatever point that is. So let's first find so this will be technically what gives us like the maximum rate of change is equals to the magnitude of that gradient vector of f. So let's first find this at a point 1, 1. So this is technically going to give us, it's a vector obviously, so it's just going to technically give us f at x partial with respect to x is this one, and you're technically going to evaluate that. You got 6, we already calculated that, so the component here is 6, and for y we also get a component of 6 as well, so that's what we have. So the maximum rate of change is just the magnitude of that. The maximum of that is just the magnitude of our gradient vector. So the magnitude of that is just the square of the components, and 6 squared plus 6 squared is just going to be 2 multiplied by 6 squared. And notice that you can take the 6 squared outside the square root. The square root of 6 squared is just going to be 6, and that magnitude is technically going to be equals to 6 root 2. And what if they also ask you like in what direction will the directional derivative be at maximum? If they ask that question, just know that the direction will be in the direction of your gradient vector. You can only find the maximum if your unit vector is also in the direction of your gradient vector. That's by definition. So this is it about like the directional derivatives. So just have your formulas in mind. This is your formula here, and then you can also do the same evaluation using like the other way you can do this is like, notice that you just have the dot product of the directional derivative. I mean, yeah, the directional, not the directional derivative, the gradient vector of f, dotted that with the unit vector. So another way you can rewrite this is just that du of f at x, du f at x naught y naught is equals to this. It's technically equals to this. Dot that with what am I doing? Okay, so du f at x naught y naught, that will just technically be this one, the gradient vector, dotted that with your unit vector. So that would be your formula for the directional derivative. You can solve it any way you like, it's still fine. So you have three formulas. You can try this one, you can also try this one, whereby you're using this, and you can also try this one. Nonetheless, you're supposed to get the same answer. You can like try the example that I did in this question and then check to see if like you can get the hang of the things. So I'm gonna upload like a second video where I work out a problem in the 2023 additional exam. Just check that out, where I work some 8-mark question there. Thanks for watching. Don't forget to share and subscribe.